Tuesday's lecture, we have seen that the so-called standing wave pattern of transmission line terminated with an arbitrary load. So for an arbitrary load, it has some resistance and reactance. The resistance part will absorb some of the incident power delivered by the generator of the transmission line. And the mismatch, that is, the difference in the characteristic impedance of the line and the impedance of the termination will introduce a non-zero reflection coefficient. As a result, we will experience the transmission line will observe the reflected wave. So the incident wave and the reflected wave, due to the difference in the magnitude and the phases, will form the so-called standing wave pattern, such as the one shown in the slide. So as to the magnitude, you see there are maximum and minimum. So where the maximum happens when the phase of the incident wave and the reflected wave are the same. So they add up and form a voltage maximum. On the other hand, if they are of opposite phase, that is 180 degree phase, have a 180 degree phase difference, they forms the minimum because the two vectors of opposite direction cancel each other. However, unlike the termination such as short termination or open termination, which reflected all the incident power, the general case for termination with an arbitrary load, the minimum, the voltage minimum as seen in this figure, does not touch zero, does not reach the voltage equals to 0 point. So what is unlike the one with short or open termination, the minimum touches the zero in the pattern. So what is the significance of this result? This result that shows that some of the energy reflected back while some of the energy goes into the termination, goes into the load. The components that goes into the node is referred to as the traveling wave. Traveling wave 就是那一个能量是可以在传输线上被行走，然后能够 deliver。反射的那个能量的整个入射，整个部分的入射能量形成所谓的 standing wave 所以以这样子的图形来看的话，我们就可以说在这一个传输线上，它有所谓的 standing wave 的部分这边 goes up and down， 也有 traveling wave 的部分，因为它没有触底，所以有一部分的能量是 deliver 到负载的所以就像这边的 remark 所说的。But anyway, as long as there is some mismatch on the termination, as long as the reflection coefficient magnitude is non-zero, you will observe the so-called standing wave pattern. And the parameter that is useful in characterize the standing wave pattern is referred to as the standing wave ratio, SWR, or sometimes referred to as the voltage VSWR. So it goes with SWR or VSWR. So the VSWR is defined as the ratio of maximum voltage, the magnitude of maximum voltage over minimum voltage. So as you can see here, for this pattern, the SWR, the VSWR, it can be found as taking the derivative, taking the division of this value over this value. And what is the SWR for the matching case? If you have a perfect matching, for the determination what is the SWR value, or what is the standing wave pattern if you have a matching mode. If you have a matching mode, then you have no standing wave component. You have only the traveling wave component, and the voltage will stay as a flat line on the transmission line. So the maximum voltage level and the minimum voltage level is the same. So the division is what? The division is 1. So if you have a matching case, then the SWR ratio is 1. On the other hand, if you have short termination or open termination, which means that you have all the incident power reflected back, then you will form some voltage maximum, and the voltage minimum is what? Is 0. Now it's touch the ground. So the division of some value over 0 is what? Is infinity. So you have some extreme cases. The minimum value of SWR is 1. The maximum value of SWR is infinity. If you have an infinity SWR value, then it suggests that it's a so-called complete standing wave. 全部都是驻波。On the other hand, if the SWR value is 1, then it suggests there is no standing wave, and it reaches the so-called matching condition. So here are some important parameters that we can derive from following experiment. 我们用做实验的方式来去，事实上这个实验我小时候也做过嘛，那结果后来回来台科大之后，其实这个电磁学实习的那个实验，其实同样的实验一直做直到大概3-4年前吧，那个马老师把那个电磁波实习的那个项目重新更新了啦，做一些比较符合没有在做那么 classical 的那个实验啦，所以我们等一下会看到一个量传输线 SWR 的实验，事实上它是非常 classical 的老古董的实验啦，我们可以看一下。那在这个实验里头呢，我们其实就要可以得到从实验的结果可以得到这3个参数包含驻波比啦，离第一个电压最小值的距离还有波长So the 3 parameters we can derive from the transmission line experiments are the standing wave ratio, the distance of first voltage minimum, and the wavelength. The 3 results will give you an idea about the property of your termination. So from the experiment, you have VSWR, you have the D minimum, the distance to the first voltage minimum, the wavelength, and the 3 will give you the magnitude and the phase of the reflection coefficient. The magnitude and the phase of the reflection coefficient. And according to the magnitude and phase of the reflection coefficient, you can calculate the load impedance ZR. So that's what we want from this experiment. By taking the experiment, you know the property of your unknown termination. So here's the illustration of the experiment. Let's take a look at the actual picture. Okay. Let's see. What the picture? Where's my picture? Okay, over here. So here is the actual picture of the experiment kit. So in the middle is a device referred to as the waveguide. So it's a metal block that the electromagnetic wave can propagate within the structure. It is also regarded as one of the transmission line type, even though that it's a little bit different from, it works a little bit different from coaxial cable or microstrip line, such kind of transmission line. And in the middle is a probe, usually an electrical field probe, that can move to the right or moves to the left. And on the top of the probe is a connector that can, this one is a BNC connector. It can connect to an oscilloscope or a VSWR meter. Well, okay, to tell the truth, I haven't used the VSWR meter before, but of course you have used oscilloscope, right? All right. So by moving the probe right to the right or to the left, you can observe the variation of the electromagnetic wave reside within the transmission line, and you can see that at certain points the swing of the sinusoidal signal becomes larger, or the other points, the other positions, the dynamic range of the sinusoidal signal becomes smaller. That is, so if you record the maximum voltage level at a different position, you will end up with the so-called standing wave pattern, as we see from the first slide. It goes up and down and up and down at the different positions. All right, so let's go back to the configuration. Right, okay, so if you move a probe right and left, you will observe the standing wave pattern. To the right of the waveguide, you can connect the end of the waveguide with a short, open, a metronome, that is, has the same characteristic impedance of the waveguide, or attenuator. 什么是 attenuator？attenuate 什么意思？缩减嘛，所以你 attenuator 是把讯号的能量缩小，所以通常 attenuator 是一个电阻啊，可以被视为电阻啊，让能量能够通过这个，它跟 matching load 的差别在于matching load 就是终端的啦，那 attenuator 通常那个元件它是一进一出的，但是讯号在进去 attenuator 的过程当中，它会耗损掉一定的比例的能量。比如说，你假如有一个1 dB 的 attenuator， 那意思就是出去的能量是进来的能量大概85%。假如你有个3 dB 的 attenuator， 那出来的能量是进去能量的一半。10 dB 呢，1/10了嘛，所以 attenuator 通常是在微波工程的实验的时候 ，attenuator 通常是拿来保护装置、保护你的那个元件跟机器的啦，那 detector 的话指的大概是 power detector 吧，或者是一些，反正这边的话，反正接头符合接头的规格，你都可以接上去，当做一个 termination。那假如说它不是 matching 的话呢，它就会有驻波所以你就会看到，当你的 probe 左右移动的时候，它不是直接看，你只要接的是示波器的话，你不会直接看到这个变化。你看到的还是示波器上看到的还是 sinusoidal signal， 但是你只要把各个地方看到的正弦波的最大值记录下来的话，就会变成这个样子。所以不同的位置最大值会变化，那把不同位置的电压最大值连起来，就形成了 standing wave pattern。OK， 而根据这个 standing wave pattern， 你第一个最容易判断的是什么？最容易判断的是什么？波长嘛。所以你只要有2个连续的 minimum， 其实不一定要 minimum 啦 ，maximum 也可以啦，或者是任何可以比照的地方只是说，我问你这个是不是正弦波？不是这个不是正弦波但那为什么你要看 minimum？ 因为 minimum 这边的斜率稍微大一点比 maximum 那边斜率稍微大一点，所以从做实验的技术来看的话，你去抓 minimum 的间隔会比较准一点比你抓 maximum 的间隔会准一点。OK， Alright, so Equation 7.26 is the definition or the formulation of standing wave ratio. As we already mentioned, standing wave ratio is defined as the ratio of maximum voltage observed on the transmission line over the minimum voltage, which can be expressed as V plus E1 plus gamma magnitude, and over V plus times 1 minus the magnitude of gamma. And it can be simplified as the things in the red dashed line box. It's 1 plus the magnitude of gamma over 1 minus the magnitude of gamma. So that's the definition of a standing wave ratio. In fact, you can, by massage the equation a little bit, you can find the magnitude of a reflection coefficient equals to what? Equals to 1 minus SWR over 1 plus SWR. So once you have derived the standing wave ratio using the experiment result, you can calculate the magnitude of reflection coefficient. Now that this result only reveals half of the characteristics of the reflection coefficient, because you only have the magnitude information. To have a complete description about a complex number, you need to have the magnitude as well as the phase of the vector. Okay, so of course we will need to perform additional tests to find the phase of the reflection coefficient. And before we do that, let's explain a little bit. As I already said, if the reflection coefficient equals to 0, that is the first case, which means what? Which means that there is no reflection. The reflection coefficient is 0, there is no reflection. The load is the same as the characteristic impedance of the transmission line. So in that case, you have the minimum standing wave ratio, which equals to 1. That's the ideal condition you can have for transmission line matching. That's the perfect case. On the other hand, if the reflection coefficient magnitude equals to 1, then it's probably the worst case scenario, which means that all the incident power get reflected from the termination. In that case, the standing wave ratio becomes infinity. That's the worst case. And what is the usage? What is the usage of standing wave ratio? Well, it can be used to characterize the characteristics of many microwave components. As the figure shows here, is the to the left is an antenna, which is useful for EMC/EMI test. That is the test for all the consumer electronics products before they go to the market. We need to pass the so-called EMI/EMC test to ensure that they do not produce noisy electromagnetic waves to interfere other products, and the electromagnetic wave produced by other products won't affect the operation of the product to be tested. And to perform the test, it's kind of a broadband test. As the figure to the right, it shows that the test band starting from 25 megahertz goes way up to about 100 megahertz. So for this equipment is used to be to perform tests between 30 megahertz to 100 megahertz. So as you can see here, the vertex axis is the VSWR ratio. So to the far left is the VSWR value is relatively large, suggests that the matching is poor, which means that the incident electromagnetic signal cannot be radiated by the antenna in the form of electromagnetic wave. On the other hand, starting from 30 megahertz goes all the way above 85 or 90 something. The SWR ratio is smaller than 10, which means that some of the incident power can radiate from the antenna. So this result satisfies the usable band of the antenna. Okay, so that's one application of the standing wave ratio. The second parameter we would like to find from the transmission line test is the distance of the first voltage minimum from the load. So what is the purpose of this test? The purpose of this test is to find out the phase, the angle of the reflection coefficient, so that using the information, using the knowledge about the magnitude and the phase of the reflection coefficient, we can completely characterize the reflection coefficient as well as the load impedance of your termination. All right, so the figure suggests that at the very beginning, that is starting from this point, this is the reflection coefficient at the very right end of the transmission line. It has a value. The value is defined as the distance from the center to the circle. Not that 有没有看到这个图哈？你要理解的是这个图上面的点是什么东西？这个图上面的点是反射系数 （reflection coefficient）， 所以它是一个 complex number， 所以它有实部有虚部，所以横轴是实部，纵轴是虚部，所以只要那个点偏离了横轴，那就是一个复数它有实部有虚部嘛。那实部跟虚部的相对位置就代表了这一个反射系数的角度所以它的这个角度是什么？它跟实数轴的夹角，所以在这边写作西塔所以西塔是那个伽马反射系数的角度那我们一开始并不知道反射系数的角度是多少，所以我们要做这个实验。怎么做呢？把这一个传输线，你看到那个 waveguide 的终端接上你这个未知负载，然后去移动那个 probe， 移动 probe 往左边走，它就会在这一个 compass plane 上面顺时针转，它会顺时针转，往左边走它会顺时针转，往右边走也就逆时针 ，OK？ 那为什么我们会取 first？ 我们要看 D minimum 呢？ First distance, the distance of first voltage minimum， 因为它比较好判断。就是说你走的时候，假如说它不是一个 matching load， 当然那个你看到的电压极值会大小变化。所以当你看到一个最小值，那当然你可能要来回看一下，来回移动一下你的 probe， 但最小值相对是容易看的啦，最小值那边的斜率比较大。所以当你看到一个最小值的时候呢，你要记录的是从一开始的地方到最小值走了多远的距离。那根据这个距离，然后去知道它的波长，就可以反推出这个西塔角。所以我们做这个实验的目的是要去量出它的西塔角。而量西塔角的方法就是看那个电压。Standing wave pattern 里头的电压最小值的位置，然后去推算它的角度，然后在这个点在这边绕一圈回到原点的回到原来位置的距离是多长？半个波长，半个波长。还记得我们看到那个 standing wave pattern 吗？我们说0点或者是电压最小点或者电压最大点的间距是什么？多少？半个波长。也就是说，走了半个波长，你会回到原来的位置。你只要从 voltage minimum 走半个波长，你会遇到 voltage minimum。那多远的距离会遇到 voltage maximum？ 1/4的波长嘛，1/4波长的一半。 所以从 voltage minimum 再走1/4的波长呢，又遇到 voltage minimum. Okay? Alright. So if you take a further look at this graph, you can find out the relationship defined in equation 7.27. So the distance, the total distance traveled in this graph is theta plus pi, because here you have a hemicircle. You have half of the revolution, so the corresponding radian is pi. Okay, so you have d minimum equals to theta plus pi times what? Times lambda. Okay, something. And the distance d equals to the phase. The phase experienced by the traveling distance d is what? Is 2 pi times d minimum. I mean the total phase change experienced in this locus equals to 2 beta times d minimum. And it equals to theta plus pi. Okay? So use this relationship, the beta equals to 2 pi over lambda. So use this relationship, you can write up equation 7.28. The minimum can be expressed as lambda over 4 pi times theta plus pi. Okay? But so eventually, what we want to know is the value theta, which can be found by knowing the wavelength lambda and the distance to the first voltage minimum. Okay? So if theta equals to 0, theta 等于0的话是在这里的哪里？在图上的哪里？在图上的最右边这一点嘛，对不对？所以第一个他们举了几个例子，当theta等于0的时候，你可能落在这一点，那它的 d minimum 会是多少？4/4派嘛，因为你走半圈。而落在这一点有什么意义？落在这一点的话呢 ，it tells us that the load impedance is purely real and is greater than the characteristic impedance of the transmission line. 所以，假如落在右边这一点的话，它是纯实数因为反射系数是纯实数嘛，所以你的 ZR 也是纯实数，而它的 ZR 值会比 Z0 来的大这个是从反射，因为你看到这一点是一个正的伽马值，所以 ZR 必须大于 Z0， 它才会是正值。反过来，假如 ZR 还是那。除了这一点是纯实数以外，哪一个点的反射系数是纯实数？还有哪一个点？左边那个点嘛。那左边那个点的话，它的反射系数是小于0的。所以那代表什么？代表上面的分子小于0，上面的分子小于0表示什么 ？ZR 小于 Z0。So if theta equals to minus pi, which suggests that the distance to the first voltage minimum is 0, then we have a load impedance ZR, which is purely real and is smaller than the characteristic impedance Z sub 0. Okay? Alright, so according to the standing wave pattern, we can find out the angle, the phase of the reflection coefficient based on the knowledge about the distance of first voltage minimum. Okay. And the third parameter, as we have already mentioned, is the distance between successive voltage minimum, which equals to half of a wavelength, 0.5 lambda, half of a wavelength. As you can see from the standing wave pattern, it's periodic signal that you have the same distance between two voltage minima, which is the same distance for two voltage maximum. However, as I already mentioned, it's easier to identify the voltage minimum. So in general, we use the voltage minimum to find out the distance between, to find out the length of the wavelengths. All right, and okay. So the following, the rest of the slide says that you can calculate those three critical parameters. I mean the standing wave ratio, the distance of first voltage minimum, and the wavelength using known transmission line properties. So assuming that, so here's an example. Assuming that the characteristic impedance of the line is 15 ohm, which is a very generous assumption, and the load of the termination is 15 minus 20J. So as you can see, it's a complex number. Now it's a more general case. So it's the resistance is 15 and the reactance is minus 20. So it can be referred to as a capacitive load. It has certain capacitance. So first you can calculate the the reflection coefficient gamma R using the formula. ZR minus Z sub 0 divided by ZR plus Z sub 0, you end up, so here is an important part about your final. 要用计算机，好不好？用计算机把复数的相乘、复数的相除还有复数的加减要算出来。那这边你会看到的是复数在乘除的时候，它比较容易使用的是 polar form。有没有听到我讲的 polar form？ 你就用极坐标的方式去表示那个 complex number 也就是 magnitude 跟 angle 来去表示。所以它在相乘除的时候，就乘就是 magnitude 相乘，然后角度相加嘛。除的时候呢 ，magnitude 相除，角度相减所以你会看到在这里原来是 real part imaginary part， 所以从这里之后，它把它换成 polar form， 8负150度除上 13.6 负17度，所以这个乘除的结果就是8除以13等于 0.6， 然后角度是150度减17度等于100。减去负17度，所以等于负133度那最后他把这个结果再把它的角度转成进度，所以变成是负 J 的 0.74 派，好不好？这个的话，你作业要自己按出来，好不好？自己还要按不然你考试那个计算机不会按也没用Alright, and once you have the reflection coefficient of the load, then you can calculate the standing wave ratio of on this transmission line using the magnitude of the reflection coefficient. So using this formula, you get the reflection standing wave ratio as what? 1.6 divided by 0.6, so that's around approximately 4, 差不多为4。And the distance of voltage minimum can be calculated using known properties. So we know that theta is what? Is minus 133 points. So it's located over here. So the d minimum is relatively small. And using this formula, you can calculate the distance as 0.065 lambda。这个结果多看几遍嘛D minimum 几个问题练习一下 ，D minimum 的最小值是多少？0嘛，只要你刚好在最左边那个点，最大值是多少？0.5， 对不对？你只要是在这个点的上面一点，那它的 D minimum 就要几乎绕一整圈，一整圈是多少？0.5个lambda。所以假如你的那个 D minimum 是 0.25 个lambda，那表示它是在这里那比 0.25 大 大就表示在上半部，比0.25小表示在下半部。所以像这个是0.065，所以它会落在哪里？落在第三象限啊。所以看了那一个D minimum的数值，你就可以大致知道你的那个反射系数 reflection coefficient 在 complex plane 的哪一个位置啊？所以它的 magnitude 是差不多0.6嘛，所以表示什么？你在所谓的 unit circle， 也就是距离等于1的那个圈圈里头，它大概是差不多落在中间了哈，0.6那个位置。Alright. Conversely, to the compilation of standing wave parameters of a given load impedance and unknown load impedance can be determined from standing wave measurements on a line of non-characteristic impedance. So starting from this slide, we will try to implement a more realistic scenario for standing wave measurement. So usually, in the usual case, we don't know the exact value of your termination. However, we can perform standing wave measurement and find out the value of your load impedance using the results, such as the standing wave ratio, the first distance of first voltage minimum, and the wavelengths. So to outline the schedule, the process, we can see that the magnitude of the reflection coefficient, that is gamma, can be written as 我这边写错了，这边写错了，好，这样也对，好不好？ The magnitude of reflection coefficient can be found by finding out the standing wave ratio, so it's SWR minus 1 over SWR plus 1. And according to the measurement, you have D minimum. So what you really want is theta, that is the angle, the phase of the reflection coefficient. Then you can, once you know the D minimum value and you know the wavelengths according to the distance between two voltage minimum, you can substitute the value into this equation and get the phase, get the angle of your reflection coefficient. So using equation 7.29 and 7.30, you have a complete description about the reflection coefficient gamma R. However, this is not the end. Now, our purpose of the measurement is to know ZR, the impedance of the termination, the impedance of load. But it's close once we have gamma R, once we have the magnitude and phase of the reflection coefficient, which is a complex number. We can substitute into equation 7.31 and get the complex number of ZR, which can be found as the product of Z sub 0 times 1 plus gamma R over 1 minus gamma R, which is, again, in general, a complex number. So using the measurement, SWR measurement, you can find out the characteristic of the termination. 所以这个 SWR 的量测的目的是要找到负载的描述，也就是负载的这个 ZR 的大小跟相位。所以一个 more general case 它是一个 complex number。而在找到从 SWR 的特性找到 ZR 的过程当中呢，我们会先算出 gamma R 反射系数一旦 gamma R 找到，那其实 ZR 就不远了Okay, so let's look at an example. In sample 7.2, using the equipment that we have just described, we have a waveguide, a movable probe, an oscilloscope, and you can change the termination at the end. So here is the procedure. The first procedure is terminate the waveguide with a short circuit. So you may wonder why we do this while using a short circuit. What happens if we have a short circuit termination? Well, it will generate a complete standing wave pattern on the line. So you should be able to observe zero voltage at a certain position on the waveguide. And by finding out the distance between successive zero voltage position, you can find out the wavelengths of the incident wave. You can find out the wavelengths, all right? And in this experiment, the problem says that the voltage minimum is found to be 20 centimeters apart. So what is the wavelength? Well, the wavelength will be 40 centimeters, okay? Because the voltage minimum appears every half a wavelength. Okay, so the next thing is replace, sorry, the next thing is mark a minimum when you use the short termination as the reference point. The reference point 我先讲一下，这是比较 tricky 的一件事情也就是说你在一开始我们说第一步是接 short， 那接 short 的话，你会看到电压零点，相邻的电压零点距离的话是半个波长，所以我们就知道一个波长的距离。但这个 short termination 的量测也有一个重要性，就是说你必须要把那个电压零点的位置 mark 起来，当做所谓的参考点。为什么我们等一下会讲到为什么。原因就是说，你看到那个 probe 是可以左右移动，但是你有没有发现一件事情？有个 bug， 就是那个 probe 左右移动的时候，它可以移动到最右边吗？它可以移动到那个接头 termination 的位置吗？注意一下它的 waveguide 的终端在这个地方，这边这种结构连接器我们叫做 flange 啦，就是它那个立起来那一片金属我们叫做 flange， 所以你的那个 short termination 是接在这个 flange 上面的。那你的 probe 怎么移动到这里嘛？没有办法移动到 flange 的位置，所以意思就是说你其实没有办法量到最右边。所以为什么要量那个参考点？为什么要 mark 那个参考点？你看到这边其实有一支铁尺帮助你去描述你的 probe 的位置，就是因为你的 probe 没办法移动到最右边但是我们又知道，当你有 short 的时候呢，它每隔20公分会重复一次，所以你的量测的位置。虽然你要量那个 d minimum， 你没有办法量到最右边，但是呢，你可以从参考点那边，反正它是周期性的，会重复出现，所以你可以把这个地方当作是 short termination 那个位置所以从那边起算，当作参考点量也是可以的所以参考点是用先前短路终端负载时所量到的电压节点当作所谓的 reference point So you can count because the movable range of the probe is limited, so we need a reference point. Alright, from the value of the SWR, we obtain that the SWR measurement result, the SWR value is 3, which means the magnitude of voltage maximum is about 3 times of the voltage minimum. And the distance between successive voltage minimum is 20 centimeters, which suggests the wavelength is 40 centimeters. And it says that the voltage minimum is found by shifting toward the load from the reference point by 5.8 centimeters. This is the most tricky part about this example problem. It says that once you change the short termination with the unknown termination, the voltage minimum, you're starting from this blue point. This is the location, this is your reference point, okay? But once you change the termination, the voltage minimum is found by moving to the right. 注意啊，这边是逆时针旋转，所以它是往右边走的。Moving to the right by 5.8 centimeter. So it tells you that effectively it's the same as moving to the left by 14.2 centimeter. 好 ，Alright. 因为它原本这个 1.8 公分啊是参靠点往右移动的结果，所以实际上你是从参靠点往左移动的话，你会走 14.2 公分才会得到 voltage minimum。好，所以这个是题目的描述上面比较 tricky 的地方所以要多看2遍 ，OK？ So alright, so according to this result, we know the distance of first voltage minimum is 14.2 centimeter, which is a little bit more than a quarter wavelength. So once you put it into the equation, you find that the theta value of your load is about 0.42 pi. 0.42 pi. So you can write up the according to the gamma magnitude and the gamma R angle, you can write up the reflection coefficient of the termination, which is 0.5 times exponential j.42 pi. All right. So theta value is found this way. All right. So here's the explanation, the illustration of the test. So the reference point is kind of shifting the y to this position. And to find out the voltage minimum, it's kind of moving to the, starting from this point, you move to the y, and you read that is the value is 5.8 centimeter, right? So it's equivalent, the voltage minimum, the distance to the first voltage minimum equals to 20 minus 5.8. Alright, so finally, you can calculate the value of ZR, your load impedance, using this equation. So if you have a 50 ohm transmission line and gamma is this, then substitute everything, you can find out it's about 77 plus 48J, okay? So you make sure that you know how to work out this number using your calculator, okay? Alright, so here using the measurement result, we can first find out the reflection coefficient in complex number form. Then substitute the reflection coefficient into this equation. You can find out the load impedance, ZR, which is also a complex number. Then, in this slide, you can find out the reflection coefficient any place on the transmission line by knowing that the reflection coefficient at a certain position, say gamma at D, can be found by taking the product of the gamma at the termination times the phase delay or phase variation due to propagation. So you see in this equation, gamma at D equals to gamma R times exponential minus J2 beta D. So what is the significance of this exponential? You see the index is 2 times beta D. So what is the significance of 2 times beta D? It means the signal goes to the Y and reflected back. The total distance traveled by the signal is 2 times d. Okay, so the phase change due to 2D propagation is beta times 2d. So the only thing you need to account is the phase, the angle adjustment due to this round trip refraction of the reflected signal. So once you know the reflection coefficient at a certain point, say gamma d, you can use gamma d to find out the impedance of a certain position, Z at d. So Z, that is the input impedance at the position d. Okay, so by definition, it's the voltage over current ratio, the impedance. But it can be found that using our known knowledge, it can be found as the product of characteristic impedance times 1 plus gamma at d divided by 1 minus gamma at d. Alright? 所以，这一章12要告诉你的是，就是我们刚刚前一页找到的是在负载的阻抗值 ZR。但我们知道，在传输线上面，尤其是无耗损传输线，不同位置的看到的 Z 值，或者说我们说不同位置所看到的输入阻抗，往右边看的输入阻抗是不一样的。但是它们其实变化的只有 magnitude， 变化的不是 magnitude 不会变化，它们的相位会变化。而同样的，你的 input impedance 所对应的反射系数也是大小不会变化，相位会变化。所以刚刚前页我们看到的是 d 等于0的 ZR， 那现在我们想要知道的是，当我给定一个 d 值，比如说 L 啦，或2分 L 啦，或L，给你一个任意的 d 值，你要怎么样找到那个位置往右边看的输入阻抗？那其实也就是2个步骤。第一个步骤，先找出它的反射系数，低那个位置的反射系数。而低那个位置的反射系数可以怎么找？由终端的反射系数加上距离的 translation 所以你看到的那个 exponential， 它其实代表的就是距离的转换而这个距离转换它是一个 round trip， 因为你看到的是反射系数嘛，所以你的反射讯号要打过去又弹回来，所以它走的距离是 d 乘上2，2倍的 d 的距离 ，OK？ 所以用这个式子，你可以找到它所对应的 d 这个位置所对应的反射系数，那再套回反射系数跟输入阻抗的关系也就这个，你就可以得到 d 那个位置的输入阻抗。而在题目的话呢，它挑的是，题目挑的是什么？题目挑的是 Z 最左边的那个反射系数 ，ZL 的反射 ，DL 的反射系数，DL 的反射系数。好，但是在讲到这个之前我们还有2页，看一下有一件事情，这边是一个好玩的事情但不是好玩而已，它也有用了The following property of the line impedance are of certain interest. At the location of a voltage maximum of the standing wave pattern, that is gamma d is a pure real number, which is so this is the condition to have a maximum voltage. The maximum voltage equals to 1 plus gamma r. It had the 我讲错了，不是。voltage maximum 发生的位置，它所对应的1加伽马 d 呢是那个伽马 d 的值会等于伽马 r 的绝对值加1，伽马 r 的绝对值加1，这是它所对应的那个最大电压的位置。 而要满足这个条件，其实是你那个 exponential minus j 2倍的贝塔 d 等于正一，好，所以它是对那个 distance d 有要求，好，好的 ，anyway， 在那一个转圈圈的最右边是你的 voltage maximum， 而它所对应的电流呢，则会在它的对面，也就是 voltage min，也就是1减伽马 r 的值，那是电流的部分，哈。那这一个位置哈，不管是 voltage minimum 或 voltage maximum， 它其实都有一个重要性，也就是它的伽马值，它的反射系数值是纯实数。反射系数值是纯实数，它所对应的结果是你的负载所看到的有效的输入阻抗也是纯实数。好，也就是说，你的负载不一定是纯实数。啊，我们刚刚看到的那个一些例子里头，你的负载可能是 complex number， 所以负载是 complex number，reflection coefficient 也是 complex number， 但是你可以把你的负载接传输线，让它绕圈圈。当你绕到最右边或绕到最左边的时候呢，你的反射系数变成纯实数，而纯实数的反射系数就会对应纯实数的输入阻抗，好，所以你可以借由连接一段传输线来去达到，把你的 complex number 的输入阻抗变成是 pure real number 的输入阻抗，好。那当然你会问说，为什么要这样做？好，那记住啊，你假如是 complex number 的话，就表示什么？你有能量 deliver 到负载，但是也有那个 reactive 的部分，电抗性的部分是储能，它没有办法，能量卡在那边没有办法传递，所以把它变成纯实数的负载，你就有机会把所有的能量都传递到你的负载去。那你会说啊，可是我们那个在转圈圈的过程，最右边的那个负载值比 Z0， 也就是传输线的 characteristic impedance 来得大，或者是最小电压值，它那个 Z 值也比 Z0 来得小，它也不是 matching 啊。那我怎么能够保证把所有的能量都能够 deliver 到负载上面去？没错，这样还不行，所以我们还要做所谓的 impedance matching， 阻抗匹配。我们要把输入阻抗变成是跟传输线的特性阻抗是一样的，我们才能够保证所有的能量都不形成驻波、不反弹，都进入到负载。但是要做到这件事情的前提是，通常一个前提是你要让你的等效输入阻抗先变成纯实数，好，所以至少在我们这边可以看到，在那个转圈圈的过程当中，电压最大跟电压最小的位置，它的等效输入阻抗都是纯实数，而其他地方都是 complex number。OK， 而这个电压最大跟电压最小的地方，它有一些有趣的特性So there are some interesting properties about the voltage maximum and voltage minimum on the transmission line. We know that, so suppose between voltage maximum and voltage minimum, the 1 plus gamma and 1 minus gamma value are both complex number, and they are now of different phase. So if Z of D is a complex number, the magnitude should be between Z times SWR and Z times minus Z over SWR. And we know that the input impedance repeat every half-hour wavelength. They repeat half-hour wavelength. And there is an interesting thing about the transmission line is if so here you have a transmission line with arbitrary termination. And here is the distance d. So the impedance observed here is ZD. And in this place is D plus a quarter wavelength, 1/4波长 quarter wavelength. There's an interesting property about the impedance at the two position. So let's begin with. So ZD can be converted to Z sub 0 times 1 plus gamma D and 1 minus gamma D. And similarly, the second input impedance, which has D equals to D plus lambda over 4. You can also write this thing up. However, because the distance at this position, so the signal will have a difference of quarter wavelengths. So 2 times beta D, let's say delta D, okay? The phase difference of these two paths equals to what? Delta D equals to a quarter wavelength. And beta equals to 2 pi over lambda. And here in the front, the round trip has a 2 over here. So what is the result? It equals to pi. So exponential minus j 2 times beta D equals to exponential minus j pi equals to minus 1. Okay? So keep this in mind. So this thing is minus 1. This thing is minus 1 as well. So the second half of the equation becomes 1 minus gamma D over 1 plus gamma D. And now that the first one is 1 plus gamma D over 1 minus gamma D. So the denominator and numerator cancel each other from this part. So you end up with the product of the two equals to what? Equals to the square of the characteristic impedance. So that's a very interesting property about position on the gamma plane. So on the gamma plane, any pair of opposite positions, the product of the impedance at these two positions, this position, this pair, the 2 points, is the same as the square of characteristic impedance Z sub 0. Okay? So this property will be used to design the so-called quarter wavelength transformer in section 7.3. 所以下一节啦，7点3节的时候，我们会讨论阻抗匹配的几个技巧，其中的一个技巧叫做1/4波长阻抗转换器，1/4波长阻抗匹配转换器啊 ，quarter wavelength transformer 好，那它的原理就是这一个哈，把那个，也就是那个转换器的长度等于1/4波长，啊，然后借由调整它的阻抗，啊，可以让我们去把距离1/4波长位置的输入阻抗变成是 Z0 啊，变成是我们要的值啦，啊。Alright, so this is an useful property. We shall learn that in the following section, 7.3. So for a line of a length L, we can find out the input impedance by using this equation, as we have seen many times before. By first calculating the reflection coefficient at this position, then you can find out the input impedance of this termination. All right. So before we leave this section, so let's take a look at example 7.3. This is kind of an easier version of the problem that you may have in the final. But in the final, you will have a more complicated problem, which accounts for loss, lossy transmission line. So in this case, it's simpler because it's a lossless transmission line. Okay. So what do we have here? So here is a transmission line. We know that the characteristic impedance of the transmission line is what? Is 50 ohm. The length is 0.725 wavelengths. What is the termination? The termination ZR equals to what? 30 plus 30J. So that's a complex number. And to the left is the generator, which has a magnitude of 100, and we assume the phase of the generator is 0 degree at the beginning. And the internal the internal impedance of the generator is 10 plus 10J. All right. So what we will do next, or what we are going to find, is list at the bottom right. So first thing is calculate the reflection coefficient at the low. Next is calculate the reflection coefficient at the input. So they are the reflection coefficient of D equal to 0 and D equal to L. Then you need to find out the input impedance. That is what? Z at L, at the input point, input end. Then you need to calculate the currents provided by the generator. That is, the current goes into the circuit using the known input impedance. Then you calculate the voltage at this point according to the current. And once you have the voltage and current at this point, you can calculate the power delivered to the transmission line system, right? So let's look at the problem. So this is kind of the basic problem that you are recommended to do yourself at home, all right? That's that's probably the simplest problem that I suppose you should be able to resolve with some practice. So first thing is compute the reflection coefficient at the low. Well, it's relatively simple. You just put them into the formula, okay? So 30 plus 40J minus 50 over 30 plus 40J plus 50. And you find out the magnitude of the reflection coefficient is 0.5, and the angle is positive 90 degrees. Then the second thing is calculate the reflection coefficient at the input to the left end, which is D equals to L. So using this formula, gamma L equals to gamma R times the propagation translation in terms of phase, in terms of angle. So exponential minus J 2 times beta times L. We know the L is what? 0.725 lambda. So you substitute the number and beta, you can convert beta as 2 pi over lambda, things like that. And the result is, of course, you can divide it by 2 pi and have the remainder of the division, right? 那个当然会超过360度啊，超过2派了当然你可以自己把2派扣掉所以 the angle of that propagation, the propagation delay experienced by this thing is minus 162 degrees, and the product is not difficult to carry out. You can find out the reflection coefficient at the left end equals to 0.5 times minus 72 degrees. Have you noticed that because the line is lossless, so the magnitude of the reflection coefficient is the same. It's 0.5 at the right end. It's also 0.5 at the left end. And in fact, the magnitude of the reflection is the same everywhere on the transmission line. The difference is the phase, which can be found using this parameter. The difference in the propagation. The difference in the propagation path result in difference in the phase of the reflection coefficient. Okay, once you have the reflection coefficient, we can calculate the input impedance, Z input impedance at the left end. So again, using the formula. So you substitute the number of gamma L, and you are supposed to use your calculator to find out the input impedance of the input impedance observed at the generator side, which is about 40 minus 50J. Alright? Okay, so once you have the input impedance, you can draw the equivalent circuit. Here you have the generator, you have the internal resistance, internal impedance of the generator, and the input impedance of this transmission line system, which has a value around 40 minus 50J. And you can calculate the currents, because using the rule you have with the circuit theory. So the currents delivered to the circuit is Vg over Zg plus Zin. So substitute the number, you end up with the magnitude of the current is 1.55 amp, and the phase is 39 degrees. Alright? And once you have the current, you can find out the voltage by considering the characteristic impedance of the transmission line. I'm sorry. No, that's not the case. But the voltage can be found by the product of the input impedance and the current. Okay? So 我刚刚讲错了所以在那个负载端的那个电压，也就是这个地方的电压这个地方的电压是用这个地方电流乘上它所看到的输入阻抗所以把刚刚那几个数字摆进来这边是 real part imaginary part 的 complex number 的粉妹了这边用的是极坐标的粉妹 polar form 所以因为它是相乘的嘛，所以用极坐标的粉妹比较容易等于 magnitude 相乘相位相加减所以你的 VL 呢是100伏负 12.6 度 OK so you can find out the voltage at the input end. So with the knowledge about the voltage and currents at the input end, you can find out the time average power observed in the transmission line system, which is uses formula that is half of the real power of the voltage times the complex conjugate of the current. 这个要注意到这个表示要 complex conjugate 嘛我们在算 complex number 的那个平均时间平均值的话会是这个因为这是正弦波 sinusoidal signal 所以它的平均值会有一个1/2在前面那你的电压乘电流嘛因为电压跟电流都是 complex number 所以你就变成是电压乘上电流的 complex conjugate 取实部就出来了 OK 所以这边你自己要回家要看过所以这边本来是正的39度因为 complex conjugate 就变成负39度所以出来是负的51度 OK 负的51度然后取 real part 的话就是乘 cosine 嘛乘 cosine 取 cosine 值得到 real part 所以出来的是结果是48瓦 48.26 瓦好吧这个自己要按过计算机知道怎么样按出来好不好Alright, and the final thing is here in the very last two slides shows the idea of the so-called normalized line impedance and normalized admittance. So impedance, Z stands for impedance, Y stands for admittance. Here you see this is a lowercase z. Unlike the capital letter Z, you have here the lowercase z stands for normalized impedance， 正规化的 impedance。什么叫正规化？也就是这条传输线，它假如是一个50欧姆的系统的话，那么你把它的 impedance 通通都除上50，就叫正规化，叫做 normalization 啊。所以，假如它的传输线系统是50欧姆的系统，那假如说你这个时候看到的输入阻抗是75欧姆，那么正规化之后是多少 ？1.5 啊。假如你是100欧姆，那正规化之后就是2啊。这个正规化的动作比较方便我们做一些系统的比较了哈，所以现在你还看不出来它的用处在哪里。不过我们这边先介绍一下它的定义，好不好？所以 normalized impedance 跟 normalized admittance 哈 is defined as the impedance is the division of the of the impedance with respect to the characteristic impedance of the transmission line. And similarly, y sub 0 y can be found by y capital Y of d over y sub 0. And also know that the admittance y is the inverse of impedance z. So you have a relationship of y equal to 1 over z. So the characteristic admittance y sub 0 equals to 1 over z sub 0, the characteristic impedance of the transmission line. So here are some of the definition. So that is the definition of normalized line admittance. So you need to remember this formulation, this relationship, okay?